Hello everyone. Today I'll be explaining a simple code which two codes which will show the difference between the performance in a normal neural network and a convolutional neural network. So this is our MNIST dataset. So we are importing the MNIST dataset. We have four different. Okay, yeah. So this is our MNIST dataset. It will be contained as an image. So this is the handwritten digit 7. In train underscore images, this will be present as a numpy array, this image, and in train underscore labels, there will be the category of the digit which it belongs to. So if the image is of 7, then it will print 7. If the image is of 2, then this will contain 2. So we divide the whole dataset into two different things. One is for training, one is for testing. We are defining a sequential model. This is to display the images, the first and second images. This is where these three lines are the most important lines. It's a really simple code actually. So we are defining 512 neurons in this dense layer, and with all of these are ReLU, and the input shape is 28 into 28. So that's the size of the input tensor, and the last layer is always softmax because we want 10 different categories. So if an image is there, so for one image there are 10 different columns, and so from 0 to 9. So if the image is of 7, so from 0 to 6 it will be 0 or some kind of value, but it will be 1 for seventh column. So it's like 10 different columns for 10 different categories, which is from 0 to 9. And we use softmax for that because it returns the probability distribution of that category amongst the others. So we use network.compile. We use RMS prop, which is root mean square error optimizer. Wait. And then this is our categorical cross entropy. Even this is used for categories, like multiple categories. There for only two categories there's binary cross entropy, and there for different situation there are different loss functions. We can use any loss function we want, but depending on the situation, which loss function we use is important. So we reshape all the numpy arrays into 60,000 and 28 into 28. So 60,000 rows and 28 into 28 columns, and we scale down the values from 0 to 255 to 0 to 1. We always do that because if most of the values are from 0 to around 20, but there's one value which is like 200. So what happens in this situation is that single error will influence the model deeply. So if it's scaled down to 0 to 1, then the influence on the model is not much compared to the previous situation. This evaluates the data based on the test images, test labels, and prints the test accuracy, which is 97%. Yeah, here we use two dense layers. Okay, the in this the only difference is the model, which is this part. Which, so we have a convolutional neural network here, a con 2D layer, a max pooling layer, convolutional layer, a max pooling layer, and then we flatten it, and then two dense layers. The explanation of the concept of convolution neural networks is basic concept is simple, is that um, so for each pixel there's a weight. So when you multiply the value of the each pixel, so if for each pixel the value is from 20 to 255, so we multiply it by the weight which is predicted using the model. So for each pixel maybe the weight is 20 or something. So it's like um con- so each pixel has its own weight, and depending on the weight, so it's an s if it's an s, and the values of the, and there's another like weights. So if the weights multiplied by the pixel values gives a higher value, then it will be s. It's harder to explain. I'll have to like draw a diagram and all, but I don't have much time. So we'll run the other. As we know, this will give a higher accuracy. Not much, but significant when compared.